looking at how we go from the graphical and verbal descriptions of kinematics relationships, velocity, time, acceleration, position, into a mathematical model. Just a little humor there. So in this video, we're going to derive and apply the kinematics equations. You can follow along. The goal here is that we will all be able to solve 1D constant acceleration problems. So just one dimension to start, algebraically, not using the graphs, although the graphs can still be a good support tool. So we are going to start with the graphical method, the way we've been thinking about this. If you imagine throwing a ball up in the air and it falling back down, it's given an initial velocity of 30 meters per second up and an acceleration due to gravity of negative 10 meters per second squared. How high up does it go? Well, you could graph this, right? You could say, if you start at 30 meters per second and you're changing that by negative 10 every second, this is what the velocity graph looks like. You can find the area under the curve until it gets to zero velocity, which is at its highest point. And you can say that's 45 meters. You could then, try to create a position time graph and see what that looks like as well, which is doable, something you could do. But perhaps we want a different way. And so our challenge today is to solve this type of problem without graphs. Keep them to help us understand what's going on, but to not rely on them, because a graph requires that you know every point what's going on at every time. And sometimes all we care about is, well, where does it get to the top, or when does it arrive? So, three different situations for one-dimensional motion that matter. The first is constant velocity. We already know how to talk about that. That's the definition of velocity, is displacement over time. We are going to talk in this video about constant acceleration, solving with kinematics equations. And then we will eventually get to acceleration that isn't constant. And for that, we'll need to go back to graphs or to using calculus. So, derivations of our kinematics equations. We don't have to reproduce these equations, but they are helpful to know how they work. And so I highly recommend that at the very least, even if you're not going to memorize them, that you kind of follow along as we go. We're going to start with our two definitions, average velocity and average acceleration. So to begin with, we start with the first definition of average velocity, change in position over time. But of course, if acceleration is constant, our criteria for these, then the average velocity is just literally the average of the initial and final velocity. Add them together, divide by 2. If we set those two equations equal to each other, we come up with a relationship that is delta x over t equals v final plus v initial over 2. You can check the units. They're both meters per second. And this, again, is only valid when a is constant, right? This kind of a graph where the velocity is changing all over the place, not going to work. The second equation we can look at is starting with the definition of average acceleration and do a similar thing. But in this case, we're just going to say, well, you could find the final velocity if you knew the initial velocity, how long it was traveling, and the acceleration rate. And if we check our units, that all makes sense. We have meters per second, which is equal to meters per second plus meters per second squared times seconds. The third equation starts again with the definition of average velocity. But this time we solve it for the final position. Say we wanted to know where will the object end up. Well, we're going to take the initial position plus the average velocity multiplied by time. But the truth is, average velocity is not a thing we can measure. It's a thing we have to calculate. So if we know the initial and final velocities, these initial and final conditions, that makes our lives a little bit easier. And so we can rearrange that equation a little bit. And we're actually going to do even more, because the truth is the final velocity is not something we usually know. If we can just put in all of our initial conditions, that will help us out. And so what we do is we say, take that equation 2 and plug it in, and then simplify everything down. And we end up with what is sort of the big equation in kinematics that you can tell your final position if you know your initial position, your initial velocity, your acceleration rate, and how long it's been traveling. And that kind of, I think, is the most logical in terms of following the process. The third equation, we start in this third equation, we check our units and we see that they all work out as well. So, equations. first equation, we don't have acceleration in it. The second equation, no position information. The third equation doesn't involve final velocity. In fact, it has no final quantities necessary to solve for the final position. And that leads us to our last equation, which ideally would not have time in it because we would like an equation every time that has a missing variable. And to derive the fourth equation, we start from the third derivation, but instead of solving in for that final velocity, replacing that, we're going to get rid of time by rearranging equation 2. Do a little more work, and we end up with this. V final squared equals V initial squared plus 2a delta x, which seems a little cumbersome, but it has the power of not revolving around time. So even if we don't know how long something has traveled, we can still say useful things. The units, again, check out. We have our full table of equations. These are on page, I think, 23 or 24, actually, in your packet. You can have those as a reference. So a couple of important restrictions. These are only used for the following things: one-dimensional motion, constant acceleration, and particles. Just a thing that we could treat as being a single point in space. But we can do that with a lot of things: a block, a car, a bicycle, even a person to some extent. As long as we're not letting things spin around at all and flex, then we're fine. How do we apply this? Well, you'll probably end up memorizing them because you use them so often. Remember, only use them for constant acceleration, one dimension at a time, and use the variables that are in the equations. Don't swap out and call the unknown x, because if your unknown is velocity, it's going to cause lots of confusion. They're all equally valid, and how do we choose? Well, we choose based on primarily the variable that we either don't need or can't find, and that's what we're going to do. So page 25 has a couple of example problems, which I'm going to go through now, and you can follow along if you like. So first example, a car traveling 90 kilometers per hour on a straight road slows down. There's that decelerate word I don't really love, but it is valid here. It just means slow down at a constant 1.6 meters per second squared. How far does the car travel before it stops, and how long does it take to stop? First thing to do is to sort of predict what's going to happen. If it's at 90 kilometers per hour, about 25 meters per second, then you can say this isn't quite 2. How long will it take to stop? You can do a quick estimate. Then we want to draw a sketch, and this is very important. We always need to have a coordinate system. Where is the positive direction? Where is the origin? So the car starts at 0 and is heading in the positive x direction. How far does it travel before it stops? This is our sketch. Doesn't have to be fancy. It doesn't have to look actually like a car, but that's the idea. The graphs are not sketches. The graphs might be useful, but they're not what we're looking for here. You can build graphs to help you, but when I say sketch, or anyone says sketch the problem, they mean this. That's a little bit confusing because sometimes we say sketch a graph, but if we don't say graph, usually we mean a diagram, a picture. So here's all the data we know. This is our next step. The variables. We want the final position. We know the initial position, the initial velocity, the final velocity, and the acceleration. We are not given time, which is exactly what we want to avoid using then. So we want the equation then that doesn't have time. And so when we're picking equations, the only one that can meet that criteria is equation 4. Then we'll do what we do when we solve problems with equations. We're going to simplify, isolate, substitute, solve, and check. So first, simplify. Anything that's 0, we cross out. We isolate. We rearrange the equation to solve it symbolically. X final equals negative v naught squared over 2a. That is the answer regardless of what v naught and a are. So that's a really powerful solution. Then we substitute in with units once and solve and make sure that that makes sense. But how long does it take to stop? Well, this is, of course, a question of time. And we know everything but time, so we can pick any equation that contains time because we've already solved for one of our missing variables. This is our simplest, v final equals v initial plus at. Solve for time, negative v initial over acceleration gives us 16 seconds. So that's that one. Another example would be a ball rolls down a ramp accelerating at a steady rate. How long does it take to reach the bottom? 8 meters from its starting point. If it starts from rest, if it has an initial speed of 3 meters per second, both of those are valid. We want to be able to solve the problem for either one. So we start with our coordinate system. This ends up being really important. If you have something that's moving at what you would think of as an angle, it's perfectly valid to shift the coordinate system so that now it's only traveling in one dimension, because it really is only traveling in one dimension, parallel to the ramp. So we don't really need to worry about components here, just one direction. We read the problem, we say, well, what do we know here? We know a bunch of things. We want the time. We know the initial position. We know the final position. We know the initial velocity and the acceleration rate. We don't know the final velocity. So we can pick an equation that doesn't have that. And our only equation that doesn't have that is our equation that starts x final equals. Cross out things that are 0. Solve for time. The square root of 2x final over a is 2 seconds. Of course, we've already solved the problem, and all we need to do now is, instead of using an initial speed of 0, use an initial speed of 3 meters per second. That changes only a small portion of our problem, giving us a quadratic. And in this case, you're going to have to plug in your values and find out what your A, B, and C coefficients are in order to solve. But once you do, you end up with 2 possible answers, 1.4 seconds and negative 2.9 seconds. Of course, negative 2.9 seconds doesn't mean anything. Things do not go backwards in time, so we pick 1.4 seconds. So that's an example of the kinematics equations and how we use them.